in having the real-time data because we saw the utility in merging that real-time data stream with the models that were being developed by Boris and collaborators. And so we've developed this entire modeling system, a somewhat refined version of the model that Boris and Alan Blumberg and others started, version of the Princeton Ocean model. Running it in real time, but also doing a lot of hindcast for various things. This is a storm surge simulation from many years ago. We utilized the modeling system to look at permitting for various water supply projects. There's a large seawater desalination facility that was built next to that big coal-fired power plant on the other side of the bay. There was concern as to what the effluent from that desalination facility was going to do to salinities in the bay, especially when combined with simultaneously withdrawing up to 30 to 40% of the river flow that flows into the bay through the main tributaries here in Hillsborough Bay. And so we used the model to investigate that, and ultimately all of those were permitted and are now functioning, and most of the predictions of change in salinity that came out of the modeling system have been verified ever since. We've also used the modeling system for hazardous material discharges or spills. This was from a discharge from an abandoned phosphate processing plant over by Port Manatee, looking at the trajectory and fate of this very high nutrient, very low pH water that was being discharged from this abandoned phosphogypsum stack. Go. We've been doing a lot of sort of basic work on trying to understand how water flushes out of the bay. This is an animation. We just took the model field and we seeded it with thousands of passive particles and allowed the flow in the bay to wash the particles around. And we basically count how long it takes to flush some fraction of those particles out of the bay or out of any particular section of the bay based on the tidal flow itself, the tidal residual circulation, that part of the circulation that's left over after you average over many tidal cycles, which is driven by the freshwater inflow and the wind forcing on the surface of the bay. And you can see here the red particles are at the surface, the green particles are in the middle of the water column, and the blue particles are near the bottom. The little arrow here tells you the wind speed and direction. And you can see as the tide comes in and out, the particles sort of slosh up and down. It's what we call a tidal excursion, which is typically 6 to 8 kilometers in Tampa Bay. But over time, there's some net movement and particles ultimately get flushed out of the bay. But it depends on where they started, how quickly they get flushed out. But on average, you can calculate a flushing rate for the bay. This is a graphic from some work that Steve Myers and I have been doing. We're looking at present-day bathymetry of the bay and the flushing rates and comparing that to 1879 bathymetry, before there were any human alterations in the bay, no causeways, no ship channel dredging, no spoil islands. So the top is present day for a very dry period, moderate freshwater inflow period, and a very high freshwater inflow period, again from observations. So the top is present and the bottom is 1879. The wiggly solid line is the number of particles as a percent or a fraction of the total number of particles introduced into the bay over time. This is a 90-day period. And then we have two functional fits. One's a straight exponential decay given by the solid line. The dashed line is an exponential decay plus a linear decay that we fit to the number of particles over time. And you can see, if you look closely, that there is some change in all three periods between pre-human influenced bathymetry and present day bathymetry, but the biggest change is during the dry period. And our conclusion is that this tidal residual, or sometimes called gravitational overturning or Pritchard type circulation that happens in estuaries, you should know that from your physical oceanography core course, is driven by the freshwater inflow, and that is not so much altered by the human changes in the bathymetry, whereas during the very dry period where there's not very much of that gravitational overturning circulation, it's simply driven by tidal excursions, and the causeways and changes in the ship channel have altered those tidal excursions to the point where the flushing is much less now during the very dry periods than it is or that was in pre-human impact days.
Mark, is that a lunar cycle that's imposed on there? You know, the sort of sinusoidal wave on the red line?
It's possible. I'm not sure, because that's, well, as you can tell from this, the way the particles are sloshed around is fairly chaotic. And so sometimes the particles will kind of converge, and other times they get swept out the mouth of the bay. And in our counting of this, and it's somewhat of a limitation in the methodology, once they go out the mouth of the bay, they never come back again. So it's possible there's some fortnightly spring neap cycle that's convoluted in there. Okay. Another project we're working on right now with, again, Steve Geiger at Fish and Wildlife Research Institute and Bill Arnold over at National Marine Fisheries Service. There's some funding to restore oyster reefs in Pensacola Bay that were destroyed in Hurricane Ivan. And so we've developed a very similar model of Pensacola Bay, and working with Eileen Hoffman and Diego Narvaez at Old Dominion University, who have a model of oyster larvae, we've been looking at the transport and fate of oyster larvae in Pensacola Bay under various scenarios. And the main point I want to make here is the left panel is simply passive advection of particles to simulate the oyster larvae movement. There's no biology involved. And you can see this is after 10 days after the larvae are released, 20 days after the larvae are released. After 20 days, they start to settle out. So wherever they are after 20 days is where they're going to likely be recruited. Whereas the left or the right panel, we've included the oyster model embedded within the particle trajectory. So for each particle, there's oyster biology included, and its growth and mortality based on information on food supply that was collected by some of the staff at FWRI. And they can also migrate vertically. So again, they can take advantage of vertical shear in the currents to ride the tide in one direction or another preferentially. And so you see some significant differences. Again, these are the identical run, except here there's oyster behavior and biology. Here there is not. So you see a very different transport and fate between the two cases. And so this is being used then to guide the restoration efforts of the oyster bars up in that part of the world. Come on. Okay. Well, again, based on our successes in Tampa Bay, and again, partly in the wake of that 1993 so-called storm of the century, several county emergency managers from Citrus County and Pasco County in particular approached us about putting real-time observations along their coastline, because people in Crystal River literally woke up with water lapping over the edge of their mattresses during that storm, completely unpredicted. And so they thought, hey, wouldn't it be a good idea to have a real-time water level gauge out along our coastline somewhere to give us more warning of that. So we put our first one at the mouth of the Homosassa River in 1995 or 96, and Peter Betzer and I, our former dean, went up to Tallahassee, and I was lugging a big Silicon Graphics workstation on a little hand truck around with me because we didn't have animations on a notebook computer in those days. And we visited the state legislature and got some money appropriated to the university to fund this coastal ocean monitoring and prediction system. Bob Weisberg was involved in that as well. And we now have several positions. Jeff Scudder is one of them in my lab. There are a few positions in Bob Weisberg's lab that are funded from that legislative initiative to put buoys and coastal stations up and down the coast of west coast of Florida. There are also some high-frequency radar surface current mappers that Weisberg's lab operates. The division of effort is that basically if it has to have an anchor, it's Weisberg's lab's problem. If it's stuck in the mud, it's my lab's problem. But all of these data have been coming in now since the late 90s. We hand them off to the NOAA National Data Buoy Center at Stennis. They do their own QA, QC, and they put them into the NOAA Gateway, so the whole world gets to play with them. And again, we have a COMPS website, or simply go to the NDBC website to find the data. Well, ports and COMPS are now components of what we call the U.S. Integrated Ocean Observing System, which is an ongoing effort that we've been involved with now since, again, the late 90s, early 2000s. I chaired the National Steering Committee of that for a while until it was absorbed into a federal advisory committee. But the goal of this Integrated Ocean Observing System is to integrate all those observations that are being made within the various regions around the country and merge those with what we call a national backbone. That's all of those measurements that the federal government makes routinely and consistently throughout U.S. waters. And that Integrated Ocean Observing System in the U.S. is our contribution to the global ocean observing system. There are people all around the globe who are trying to do similar sorts of things. Again, integrating satellite data with models, with in situ data to provide a comprehensive picture of what's happening now in the oceans. And I'm running out of time, so I just want to quickly show, this is all the real-time observations around Florida that you can get from the NDBC website. All the yellow ones are COMPS sites, all of these along the coast, and then these offshore buoys here are all operated by us. Again, the offshore ones by Weisberg's lab, the onshore ones by my lab, primarily Jeff Scudder. This is the tide gauge that sits right over across the harbor here at the Coast Guard base. Looks like a porta potty on stilts, but there's an acoustic water level gauge in there that sends pings down a tube, and by measuring the round trip travel time of those pings reflecting off the water surface, computes the water level to very high precision. Just to illustrate some recent history, this is Tropical Storm Debbie that came through here. It was basically an unprecedented storm that came through. It stalled just offshore, and so we had southwesterly winds for about 3 or 4 days. Again, the blue line is the predicted from the astronomical tides. The red line is the observed water level, and the green line is the difference between the two. So the red line would be the storm tide, the green line would be the storm surge. So we had a storm surge of 3 to 3.5 feet, about a meter above predicted tide, that persisted for 3 days. I couldn't get out of my house for 3 days. So fortunately we didn't lose power, and we had plenty of rum, so we were in good shape. But again, we're looking at all the tide gauge records up the west coast of Florida to try to understand how that surge evolved and how much of it was driven directly by the winds, how much was driven by Ekman transport from offshore. Got a summer intern that worked that up, but we haven't followed through on it yet. So anyway, I don't want to take too much more time. I just quickly want to talk about an effort that we're doing, again, in support of this National Ocean Observing System. a lot of it is governed, a lot of what we can measure is governed by technology. These are all the so-called core variables that we would like to measure as part of a comprehensive ocean observing system.